kind of the basic physics sequence was taught by a very famous experimentalist who got Nobel Prize, etc. But he was a terrible teacher. So I decided, I'm not going to be experimentalist. These guys don't understand anything. Let me look at Landau Lifshitz. Landau Lifshitz starts with a very thin book called Mechanics. And, my mechanics has always been a ladder leans on the wall at 45 degrees. What happens? Not Landau Lifshitz. It starts with Lagrangian on a page 1 and variational principles. So it's a very thin book, but it's very sobering and very beautiful. So I started reading that. That was so beautiful and wasn't boring at all. So it really was one of the reasons why I chose to do physics. So now time has come to speak of the things that are no longer required. But, all our science comes from them. And it starts with Babylonians. It certainly is done by Greeks. They did epicycles, which we tend to laugh about. They said orbits of things, planets were sums of little circles running on top of little circles. And actually, that's what we actually do today. It's called perturbation theory. So we piece complicated behavior from bits which are perturbative. But the things really changed with Newton, incredibly brilliant assistant professor in the pandemic year. So in pandemic year, he wrote Newton's law, which said acceleration, so mass times second derivative of position in time, equals force. In my defense, I have to say I got up at 1:30 a.m. because I'm nominally in Germany. So my brain is, on German time. So he said mass times acceleration equals force. And the force he had in mind in the first round, the simplest version of it, was, no time dependence. There isn't somebody turning the wheel outside. And a great idealization, which Aristotle was not brave enough to make, no friction. Now that's a crazy thing to do because, obviously not true in our world. Were it not for Galileo, who established that objects of different mass fall at the same velocity, even though they were falling in air. So that's a Newton law. And there's a beautiful version of it, which we will describe without describing. But the crude version is that, this is a vector, three-dimensional thing. So this is a vector. So force points someplace. So there are three components to this law in our ordinary world. And if there are several bodies, the number multiplies very fast of components. But this vector can often be written as a gradient of a function called potential. Now that's a big deal because that's just a function scalar thing, it just returns a number. But when you vary it, you actually get a vectorial law. So in that version, Newton's mechanics why was he allowed to forget friction? He was thinking of celestial bodies. And friction is a negligible case in motions of planets. It exists, but it's not a big deal. And out of that came something very contentious, which we'll derive, by a quick argument, but they're much more elegant arguments. If you multiply both sides of this equation by velocity, so now we are pretending that the world is one-dimensional. There's only one x, but this works also in arbitrary dimension. There you dot this object by velocity, vector times dot product. Then you observe that if you write 1/2 and velocity square plus potential and take its time derivative, then you get this expression because, taking derivative here brings 2 down and a second derivative of one of the terms. And v only depends on x. So taking derivative of v means you have to take a gradient of v and dot it with x velocity. So it turns out that there is a conserved quantity. So if you take kinetic energy, mass times velocity square, and you add potential to it, potential energy, if the problem is separable. Now, the beautiful version of this doesn't require the separable quantity. This is preserved, and when you think what it means is, this is a vector field. So if you're taking derivative along the direction of it, which means on the trajectory, what's in the brackets is conserved. More specifically, it's conserved on a trajectory that your system evolves, your moon moves around the Earth, a satellite around the Earth. This quantity, called energy, is conserved. So this is not obvious, and it goes against our ordinary experience where we, drop something into honey. Viscous systems, it's clearly wrong, but it's a very good approximation to lots of things. And, there used to be a time when this was actually a spring or a pendulum. So an example of energy conserved system, and the main trick was how to compensate for the friction in such a way, how to drive the system in such a way that you don't change its frequency. So now let's work out a little example of this, which is a very good example for lots of things that we see, let's say, in low temperature physics or lasers or many other physical systems, not Newtonian gravity, that's not what it is, where we write potential to be a function proportional to x squared. So that means when you take derivative of it, you get something that's linear in x. That's called Hooke's law. You push something, and it's supposed to push against you, except we'll write it with the wrong sign. So what happens, we push, and it doesn't oppose me, it just goes on. So it's kind of an anti-spring, but you'll see it's not so strange. Now that would be a terrible system because that would just accelerate without the end. So we have to compensate for this when the harmonic thing is overstretched. We have to put a nonlinear term. And you will be tempted to put x cubed here, but x cubed is not allowed by physicists because x cubed is going down on the left and going up on the right. So there is difference between left and right. And usually in physics, it's not obvious what I should call right or what I should call left. So you have to write an even function here. So this is the most popular even function. When you start doing quantum field theory, this will be called 5-4 scalar field theory, but right now it's just called anharmonic oscillator. It has harmonic term. Harmonic means harmony, means regular oscillation, but this changes it. And if you put here higher and higher powers, it will be an interesting potential because if x is smaller than 1, then this is almost 0. And if x is larger than 1, then it explodes. So there's a nice limit of this x to infinity potential, which is called a wall or a mirror. Meaning on one side, you don't feel it at all because it's so small, it's 0. On the other side, it's infinite. So no matter what energy you have, once you get to the wall, you have to turn around. And that's what gives us mirrors, etc. So here is one version of this. Simplest anharmonicity, consistent with the symmetry, assumed symmetry of the world. Now the force is a gradient, so it's cubic, and it does care about left and right. And Newton says this is the acceleration. So at this point, our story visits, what's unattainable for most of us. Already, we are already burned out for it. In Ireland, in the beginning of 19th century, there was a prodigy. Now, the Brits are big on prodigies. John Stuart Mill is another example. So what happens to prodigies? If you're an Indian prodigy in the United States, you compete in spelling bees. But at that time, there was always an uncle who made sure that you learned when you were 3 years old, that you learned at least Latin and Greek. And by the time you're 10 or 11, you would be speaking at least 12 to 20 languages, Aramaic, all that languages you can imagine. So that happened to a poor kid called Hamilton. He had an uncle, and at age 13, he had a nervous breakdown, as they always do. And for relaxation, he decided, I'm tired of all these stupid languages. Let me think of optics. It was a fashionable subject in Science magazine of the time. The light reflects and, it's a cute thing. And let me think about it. And he formulated optics in a novel way, which a few years later, he realized all of mechanics can be written in this novel way. And he revolutionized the way we thought about mechanics. And that's called Hamiltonian formulation that you will never learn because it's not required. So I'll give you a little hint of it. It's both beautiful and awkward. But what he did is, he did what we are teaching you here. He rewrote these equations as dynamical system. So he said, well, one of the equation, x dot equals y, I just call it new thing. This y really means velocity, right? So there's velocity. Now, change of velocity in time is called acceleration. And that's, this force is kicking us or pushing us. So whenever you have a mechanical system, you always have an option of writing Newton's law as a pair of equations that are first order. And the fancier version, teaches you that you should really use not velocity, but momentum here, which in this simple case is m times velocity, but it's, profoundly different in more complicated, more realistic cases. And then independent of this, there was another way of generalizing Newton's law here, which is called Lagrangian formulation. And in 20th century, both became very important. Hamilton formulation turned out to be a core. If you ever take quantum mechanics, the simplest, quantum mechanics in which you have space and time as separate things is naturally written as Hamilton's form, basically because Hamilton started with wave mechanics in developing his formulation. He didn't know there would be quantum mechanics a century later, but it turned out to be incredibly useful. Now, if you get stuck in Hamilton formulation, space and time will always be different for you. You'll get stuck roughly in, let's say, 1920. That's all a little bit late, but it turns out when you have relativity, gravitation, special relativity, general relativity, quantum field theory, then actually the other formulation, which is called Lagrangian formulation, or if you engineer designing robots with constraints on joints, you don't want to use Hamilton, it's too awkward. You use Lagrangian formulation. So both of them are very ancient. And we know when we have dynamical systems, what do we have to do? Well, we have to look for equilibria. X equals 0 is obviously an equilibrium. You want velocity to be 0. So X is one possibility, but you know what cubic looks like. It goes up and goes down and goes up when there is a minus sign here. In this case, it comes from up and goes down on the right-hand side. So there should be two more equilibria, and they happen to be at if X is 1. And this has a symmetry by reflecting both X and Y axis. This cubic is nicely centered. So if I put X equals -1, it'll also cancel. So these are the equilibria, but then you know that whenever you have equilibria, you also have to understand their stability. Stability is matrix of velocity gradients. So these are velocities, you take derivative. With respect to X, you get 0. With respect to Y, you get 1. With respect to X here you get 1. And here you get -3 times X squared 0. And then we are supposed to look at the eigenvalues of this thing, how to do it, to construct a phase portrait. So you have 3 equilibria. You have matrix of velocity gradients, which evaluated on equilibrium is just a constant matrix of numbers. In general, it's a function of X, but on equilibrium, it's constant. And there are 3 equilibria. So there is 0, 0, the guy at the origin. This goes to 0, so it's 0, 1, 1, 0. The trace of this thing is 0. You have to solve quadratic equation to get eigenvalues. Determinant of this thing is 0, -1. You stick it into your quadratic equation, and constant term is 0, and the trace 0 is 0. So you find out there are 2 eigenvalues, and they are -1 and 1. So this thing is hyperbolic origin. And we can draw it. So here is y equals x dot. That's the displacement x. And this guy, when you work out eigenvectors, one of them points this way. And the other one, and it's unstable because one of these guys this is stable, this is unstable. So you draw a local portrait, hyperbolic system. Then you have to deal with 1, 0, and -1, 0. Now, sign doesn't matter, so they'll have the same stability matrix, which will have -2 here. Pretty soon you'll realize, well, doesn't matter. Same stability. So trace is still 0, but determinant is positive. Now remember, you have to take trace square -4 times determinant. So this is going to be imaginary eigenvalues, and that's what we call the center. And they are at 1 and -1, so they're symmetrically placed. And what happens around them is that very close to them, you're practically on a circle. Then this gets kind of deformed. And that is the last one, which has a property, that its velocity starts out as 0. So it takes infinite time to get started. But if you perturb it a little bit, it'll move. And it'll come back. So there is a separate tricks between running around here and running outside here. And on this side, similar thing will happen. Just a mirror image of what you see on the right-hand side, because left and right are the same. So there are 3 kinds of behavior. There is oscillations about one of the equilibria, either one. You just run in a little circle, you oscillate gently. And it could be this guy or the other guys, doesn't matter. Then there is a very special critical value for which it takes you forever to get started. Once you get started, you run roughly with the same velocity as everybody else, and then you take an infinity of time to get back. That's called a homoclinic. trajectory, homo for same, Greek word for same, and cline is like in inclination, the same. So what that thing does is you start at equilibrium, and that thing lands at equilibrium. Now it can, make its mind whether it's running this way or it's going to run around the both things. It's very indecisive, and that's why it takes infinite time to do that. I won't do this in much detail, but Strogas does it very well. Linear analysis tells you there is a center, but center is a very fragile thing. It's for very special values of parameters. And when you do nonlinear analysis, sometimes you find that you spiral in and out and stuff like that. We did that last time. But, or at least Strogas does it if I missed it. But you can now prove theorems that because of energy conservation, you have no choice but to be a center, run around in a circle. You're not allowed to go down into a fixed point or equilibrium, because if you do this energy, I'll draw some pictures to make it more obvious, energy will be changing. Or if energy is not changing, the energy is constant, so potential is constant, so you don't have an interesting system. So that's, the basic structure of this double well potential. Now, why is it called double well? There are other ways to draw it, so I'll draw it in a few ways that look nice to me. So I can draw this quartic function, and I can imagine that this is, a one-dimensional mountain chain. I've cut through a mountain chain, but I'm only allowed to move in one direction. So potential function is looking something like that. There is above and below of the potential. I'm not allowed to go deeper than this potential allows me. So if I take a little particle and roll it down, what will happen to it? It'll speed up until it gets to the bottom, then start slowing down until it gets the same potential thing, because total energy is conserved. And then I'll come back. That's called a libration. A word from celestial mechanics, but that just means that when I stop, I just go back and retrace the same spatial trajectory, but with the opposite velocity. So once I go up and once I go down, and because the system is energy conserving, I never stop bouncing around. Now, around here, the thing looks like x squared in this neighborhood, but it's the top of the mountain. So, it's an unstable equilibrium, because if I bounce a little bit away, I'll never come back. And on the right-hand side, I have this x to the fourth dominates. So this has the wrong sign, but this has a sign that says I'm always bounded. I cannot go, for any finite energy, I cannot go very far enough. So that's one way to think of these systems, by just drawing the potential. And, that's natural for these systems where I've decided that kinetic energy and potential energy are separate. Or I can take position plane and velocity plane, So this is a two-dimensional plane, and then I can plot the function. It's still possible when I have functions, scalar function of 2 dimensions. Humans can still visualize that. The energy function. The energy function is the one we wrote here. So it depends on velocity or y coordinate, and depends on potential or x coordinate. And if I plot that, I'll find out that there is always a surface that I'm confined to. That's called energy shell. Two-dimensional surface in this case. And this is the easiest way to understand why in dynamical systems, you don't think in terms of vector spaces, all direction be the same. You think in terms of manifolds. Because the conservation law forces you to sit on a curved surface, energy shell. And what happens on this energy shell is that here you have the bottoms, and here you have the top, someplace there. And now when you're close to one of these bottom things, you have to rotate on the energy shell. You run at a constant energy. If you're here, so it's same energy, there are two solutions which are disconnected. You're either close to this equilibrium, close to that equilibrium. You cannot have less energy than the bottom of this thing. Then there is the separatrix. If you just right here, you run around in infinite time on either side of this thing, and you come back at infinite time. Now you would think, okay, infinite time, who cares? But it's very, very important in a study of chemical systems and where you study dissociation and the role in which quantum mechanics or wave mechanics affects that. That's called tunneling. So this is the simplest example mechanical example where you can study that kind of mechanics, or what happens if there is some stochastic component, there's some noise. But in deterministic mechanics, you can see that there are three kinds of behaviors. Either you're caught up in one of these, valleys or holes, or you are undecided, so you are just exactly at the tip of the unstable mountain. So this unstable thing is pretty important if you draw it this way. Or you just run around and you don't realize that it's finite structure. So if you go very high up, this will look like a circle because the quadratic term will be negligible compared to quartic term. So that's a nice example of energy conserving system, or what we call classical mechanics, a subject that you don't need to learn. Then there's an interesting twist to all this, which is called reversal symmetry. The simplest example of its time reversal. And time reversal says, if I happen to have a potential such that if I change the direction of time, so I was progressing in time, now I'm regressing in time. But potential equation, the second equation here, this one, the velocity equation, has a property that I can also reverse minus velocity without changing my energy. So my invariance is still there. My energy is sacred, because if I change time and velocity, this doesn't change sign, this doesn't change sign, so everything is good. Then magical things happen, and they were very perplexing in 19th century, because in 19th century, people like Maxwell and Boltzmann explained thermodynamics. Thermodynamics is a beautiful subject, apparently much hated by undergraduates, but it's an amazing subject because they were just making steam engines when they, put together thermodynamics. They knew nothing. They knew not about atomic natures, about molecules. They knew some chemistry, but not much. But they needed to make steam engines, and just by pure thinking, they invented thermodynamics, which requires almost nothing but pure thinking to write down. So it's a beautiful thing. But in 19th century, it became obvious that we are looking at gases, molecules, etc. So one had to explain thermodynamics. And one thing that happens in thermodynamics is that, entropy increases. The things, there is no perpetuum mobile. We cannot extract the energy that we put into system out of system, because it gets dissipated in random motions of molecules. But how is it possible if you have time reversal? So that led maybe to suicide of Ludwig Boltzmann, who was, harassed endlessly, but he was correct in his formulation. Or maybe he was just a depressed physicist, which happens. But it was very contentious, the symmetry. And, there's nothing to argue for small dynamical systems. You have a system that has this form, and acceleration is given by force such that this is the same as force of x being relabeled left and right. Now, the potential that we started with has that form. If I change x to minus x, this is squares, nothing changes. That's why we have x to the 4 and not x to the cube here, the guiding principle. If you have that kind of system, then what will happen is when you plot its phase portrait, so here is velocity, here is position, and you work very hard. The Norwegians who computed trajectories of charged particles at the beginning of century to explain polar lights. Lots of labor can go into computing a piece of trajectory that's moving this way. Now, this principle says that if I change v to minus v, that means here, I should get a solution because the thing is invariant. So there should be a solution that looks like that. But then I have to change the direction of velocity because the time is progressing. So this arrow goes the other way. So that means that time reversal invariance says I have to only compute, roughly speaking, half of the trajectories because other half is known. And that turns out to be very useful. And believe it or not, I'll talk about time reversal in Germany, where I am currently on Thursday I'll give a talk about, how amazing it is, which is hard to believe, but it's still true. And what this now does, it's done well in Strogatz. I won't do it myself because you only have so much time. That if I have a center, this thing forces crossing the center at 90 degrees because you want the thing to be smooth. And if you cross the velocity equals 0 line, 2 places, then you're forced to, by this reflection symmetry, to go through the repeat of this thing on the other side with, of course, velocity reversal moving in the same direction. And that excludes, again, that's called nonlinear stability. When you have reversibility, you don't have possibility that this center is spiral in and spiral out if you do nonlinear analysis of a problem. It's nonlinear stable, it's robust. So that's one thing. And then, most things that you will see in your education or research, unless there are magnetic fields involved, will have this property that left is same as right. So they will be reversible Hamiltonian systems. And then you might think that if I have reversibility, I must have conservation because most examples look like that. Not at all, they're distinct. So here is an example of a two-dimensional system with velocity. So now, there is no potential or energy function that gives me the system. It just shows up in modeling some or other problem. And you experience periodic forcing in these variables x and y. So in some sense, these are angles, even though I'm writing them as x and y. This has reversibility in the following sense. If t goes to minus t, then left-hand side change their sign because the derivative with respect to time. But now if I take x goes to minus x, then these guys change signs, right? Because, well, they don't change sign, but both time and position change sign. So left-hand side doesn't change under this. But then I have to do something with y. And if I also decide to reverse y, everybody is invariant under this. Now, what does this mean? X goes to minus x, y goes to minus y. That's basically rotation by 180 degrees. So that's perfectly good symmetry. It says I have a system where x and y are pretty much democratic, and I turn the plane by 180 degrees or by pi, and the law is invariant in this. There is a very famous example called Lorentz attractor that we'll come to that has the symmetry. But we are told the following thing. We are supposed to find equilibrium. Equilibrium just requires that cosine x equals 2 cosine y, 2 cosine y equals 2 cosine x, which if I multiply by 2 and subtract, tells me that I have to look at, okay, 2 2 cosine x is minus cosine y. And the same equation other way around works if cosines are all 0. So if all cosines are 0, there are 4 fixed points, plus minus pi over 2, plus minus pi over 2. Then A is, as I take derivatives, I get signs all over the place. I get 2 sine x star 2 sine y star fixed point and sine y sine x. And this has to be evaluated at 4 possible places. So it says in this x and y plane, in units of pi over 2, there are 4 points. This is pi over 2, 90 degrees. Here and here, there's a fixed point, there's a fixed point, there's a fixed point, there's a fixed point. And now I have to evaluate these things in 4 fixed points. So let's look at this guy. So let's look at minus pi over 2, minus pi over 2. In that case, stability matrix is minus 2, minus 1. So that's the matrix. So its trace is minus 4. So it's not going to be a center because it has, real part. And this is 4 minus 1, so determinant is 3. So that's a saddle point. And then when you look at the formula for the roots, all 4 roots will turn out to be negative. This delta is not big enough to counteract this very large offset here. So one finds out that there is a heteroclinic connection. So it's hetero. Hetero means different, of different sex. Clinic is inclination again. And this guy is attractive. And the other ones turn out to be all hyperbolic points. And they are connected by heteroclinics. So this one turns out to go this way. If you're on the wrong side of it, there is a symmetry. It'll turn out to go this way. So this one has one attractive direction. That means the other direction will have to be unstable. Will go in here. This one goes in here. And then, there is a stable direction here, but unstable this way, but then you meet the saddle point, you split. So you get this heteroclinic web where everybody more or less ends in this hole down here. But we have just argued that for conservative systems, you cannot end up in a hole. You have to, oscillate. There is no way up and down. So this is definitely not conservative system. But reversibility enables you to prove many things, and you now understand how everything is going to look like. So everybody, so let's see, all these orange guys are exactly heteroclinic. But then actually, because there is a hole, everybody falls in a hole. So there are lots of things that fall into the hole. This trajectory go that way, this trajectory go that way. But if you're too far away, you will go and be rejected this way or that way. But if you're within this regime, you'll be falling inside. It's an example of a reversible system which is not conservative. This says system is same if I rotate X and Y plane by 180 degrees like this. And if I reverse direction of all errors, because time goes to minus time. So this is the system. It has its 4 points. I rotate it by 180 degrees. It looks the same. But now I have to reverse these directions of eigenvectors. So this becomes unstable, this becomes stable, and these are still hyperbolic points. So that's how you see the system is reversible. It has a totally obvious symmetry in its phase portrait. It's this 180 degree symmetry and reverse all the errors. So that sort of says I only need to compute half of the system because I can construct the other half by time reversal just by rotating 180 degrees. So that's what's useful about reversible system, even though it's not conservative. Let's look at the pendulum. It's not an easy system. You might think this is the easiest thing, but it requires a bit of mathematics that, for example, I have never gone through myself, I have to admit, to write analytic solutions for the pendulum systems. The pendulum has a length. At the end of the length, there's a joint. But this joint should not be blocked because we want to be able to move in all directions. Then there is an angle from a resting point. Resting point would be just pendulum hanging down. So this is an angle from it. And we assume there is gravitational force, G. And the equation of the pendulum is acceleration. Now the length is constant, so the only thing is angular acceleration that changes. And then there's this force. Depends how long this thing is. So gravitational acceleration over length. This is pure number, so that's why this has an extra length here. And the force only depends on the projection in the vertical direction of sine theta. And acceleration and force balance itself according to Newton. So now this is conveniently rewritten by renaming this thing omega, which turns out to be frequency. And then you have a freedom of rescaling your units of time. So you can choose to be in units where you have 1 beat per omega time. And now you have a nice pure rescaled equation with no parameters. Hamilton says, write this as 2 linear equations. One that says angular velocity is something, and the other one says that acceleration derivative of angular velocity is minus sine theta. So no acceleration at the bottom, most acceleration when you're horizontal. We always have to find fixed points. So where are the fixed points? Or equilibria, the way I like to call them. V fixed point should be 0, but theta should be such a sine of theta is 0. And that happens when theta is 0 or pi or any multiple of pi. Theta is modulo 2 pi because we measure angle as well as we can on a circle. So, well, in principle, this can be any k. K equals 1 is good enough for government work. We have 2 possible 0. Either k equals 0 for fixed points. So there is a 0, 0. Or it's pi. And the stability matrix that's derivative of this. So this gets turned into a cosine. So this doesn't depend on theta, 0 here. This doesn't depend on v, 0 here. There is 1 here. And when you take derivative of sine, you get cosine. Evaluate at theta, you get -1. Now, when you do this for the other equilibrium, this is all the same, except now you're evaluating sine at pi, which makes it 1. Both of them have trace equals 0, but this one has a determinant 1, so that has to be a center, because square root of 0 minus negative quantity, minus positive quantity, that's imaginary. So this is a center. Now this other guy, when you solve it, there are 2 eigenvalues, lambda 1, lambda 2. -1, 1 are the 2 eigenvalues. So this is a center and this is a saddle. Now we have the first go at a portrait of pendulum phase space. It says, as I look at theta, and here at theta dot, we have energy conservation. This is mechanical system, so it's angular velocity square plus the potential is conserved. This guy at the origin is supposed to be centered. This is a saddle. So at the origin, I do close to the origin, I run in the circles. And then there are 2 unstable things. So this is a center. And they turn out to have eigenvectors. You can check that. That look like this. Come in, go out. Come in, go out. And now there is a 2 pi periodicity in this problem. So this guy is repeated here. And if you want to be boring, and we did it at the very beginning of the course, you can just draw lots of these guys, but theta really makes sense, from 0 to 2 pi or from minus pi to 2 pi. So what can we now get to say about more global structure of this? And what will happen, and this is very precarious, but happens in this for pendulum, is that, and it's due to symmetry, is that there'll be special thing that if I go out in the unstable direction, I'll fall into the stable direction here. And if I go here in unstable direction, I'll go in stable direction here. And you would say, well, that's a heteroclinic, but it's not heteroclinic because this is the same point. So there is a center here. I'll run like that. And outside, this is a very special trajectory. I start here in a hyperbolic point, which is at vertical pendulum. The stable pendulum hangs like this. 180 degrees of pi rotation is vertical. And at glacial pace, by quantum fluctuation, the thing will start moving and take very, very long time to leave this equilibrium point, speed up like crazy, and then end up coming back to the tip. So that's the interpretation of the homoclinic part. And physically, it's obviously there's only one vertical possession, so I'm returning to it. But my picture says there are two, so what's wrong with my picture? So what's happening here, I oscillate around the normal equilibrium. Here I've given this thing too much rotation, so it just keeps slowing down, falling, slowing down, so it keeps tumbling. So up here I have full rotations of the pendulum. Down here I have vibrations of the pendulum. And to understand what this means, when you get into this silly stuff that seems pedantic, but it's actually quite important. You have to understand that when you have a periodic system in angle, then you have to think of the phase space as existing on a circle. And you have to do this thing where if you include this point in your definition, then you have to exclude it from this side because that happens only once. So let me draw it a little bit in a more persuasive way. So here I'll draw it on a graph paper. So we have an equilibrium here, center. And here we have unstable hyperbolic point. We have a heteroclinic thing. Well, homoclinic, but it looks heteroclinic. That I leave on the unstable manifold, I end up on a stable manifold here. And then we have rotations of the whole pendulum and oscillations of the whole pendulum. And the way you're supposed to think of this thing is, you're supposed to roll it up in a cylinder and identify the pi point the natural phase space for oscillatory system is cylindrical. So it's, you know, if I try to draw it in some kind of perspective, it looks like that. And then my trajectories, my equilibria are someplace here, center, and I run around this way. And then there is a thing that I have to go behind to see it. And the other things, you know, run this way and this way, that way. Another way, which is more useful still, is to draw an energy portrait. Now, what happens in energy portraits, you know, kinetic energy going this way and going that way are the same. So I'm supposed to bend this cylinder, so I can't do this with my paper because it's not very rubbery. But I'm supposed to bend the negative energies and positive energies. And I'll get something like this. So energy manifold has a bottom, has a special point. So down here, that's called libration. You just go duk, 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 duk. So I retrace myself down here. Now here I run that way. And that means that when I get here, I'm running the opposite way. So it has to be horizontal. So here I have clockwise pendulum running around. Here I have anti-clockwise. And this is all, you know, different sections of theta and theta dot plane. But it's an energy portrait. Then I'm done, but here is just a little picture that's helpful. Suppose I add friction. That immediately makes it not mechanical system, not Hamiltonian, not Lagrangian, none of those beautiful things. Where B larger than 0 is damping strength. Now, if I look at the energy function, so I look at dE dt, energy function was kinetic energy plus potential energy. Taking derivatives, I get overall velocity times second derivative here, and this becomes plus sine theta. This is the same as minus b theta, right? Because it has opposites. So this becomes minus v velocity squared. So this is strictly positive, and this is strictly positive. So the energy is changing with time. It's getting smaller and smaller. And if I draw the same energy picture that I've drawn before, what will happen is my trajectory will start out, but it's losing energy. So re-emerge lower, and it'll end up here. And then very slowly, it'll eventually end up there at infinite time, but finite time for any finite precision, right? So that's all we need to know for now about mechanics as a special example of dynamical systems.